Ladies and gentlemen, my name is Angelos Mavros. I come from Athens, Greece. I am a professional music producer and marketer and a hobbyist programmer. If you don't understand my lousy accent, switch on the subtitles. I include subtitles in all my videos. In this video we are going to explore the ZX81 computer, and for that purpose I found a beautiful Sony television from 1972, which is perfect for the ZX81 because it is monochrome as the ZX81. It is a portable TV model 110, manufactured in Japan and consists of 27 transistors. The ZX81 has a Z80 CPU running at 3.25 MHz. It can display 24 lines by 32 characters or 64 by 44 pixels. It has an 8 kilobyte ROM and 1K internal RAM, which can be expanded to 16K. It was released in March 5th of the year 1981 and discontinued in 84. The ZX81 was the direct successor of the ZX80, which had also a monochrome display on UHF television. The ZX81 is a home computer that was created by Clive Sinclair and released by his company, Sinclair Research. It is a British computer. Sinclair Research was based in England. The video output was meant for a television set rather than a dedicated monitor, and programs were loaded and saved onto tape cassettes. Clive Sinclair and his company were very successful. They were the low-cost competitors of the giants like Apple and IBM. He was the only true rival of the big guys, and the ZX81 has fans all over the world till today, 41 years after its initial release. As you can see, there are only 3 onboard chips: the Z80 microprocessor from NEC, a ULA chip from Ferranti, and an 8 kilobyte ROM where a simple basic interpreter was stored. There are 2 ways to create software for the ZX81. The easiest way is to write code in BASIC language, and the hardest way is to write the code in the assembly language that the Z80 understands. So I went on eBay and I found a Sinclair ZX81 that was on auction. This was my first attempt to buy something that is on auction. The product looked in good condition. It said that it was operational. It was 5 or 6 o'clock in the afternoon, local time, and the auction was ending around 1 o'clock at night. The starting price was 30 British pounds, and 2 guys had already bid. My first thought was not to bid, because I figured that the more people bid, the higher the price will go. So I thought perhaps it would be wise to bid when the auction was about to end. But then I considered some other factors and came to the conclusion that this was not the wise thing to do. The right thing to do is to be the aggressor and bid directly, because if everyone is thinking in the same way, everybody will jump to bid the last minutes or the last seconds, and this will create a haze, confusion, and who knows who will eventually win the auction. So I just had to bid to ensure that I can claim the product. For some reason I pressed the button twice and increased the price to 34 British pounds. And then another guy showed his teeth, and then I overcame him immediately, and the time was 7 and 21 minutes local time. After that I was just waiting, but I said to myself, don't go to bed, because there might be some prick who thinks in the way that I described earlier, and he might jump in last minute or last second thinking that I might be asleep or away. But I outsmarted him, because I didn't go to sleep. And thank God I did that, because the prick bid in the very few last seconds. And then I bid again, and he bid on top of me 2 times. And then you see these 3 here because I was in panic, pressing the button like crazy. And that is why you should be the aggressor, because you might not be calm enough to make the correct decision and mess up. So I got the computer and it turned out fine. In this video we are going to mess around with 2 games, one written in basic language and one written in assembly. We will move over to a real ZX81, the game written in basic language, through a smartphone after converting it to a sound file. As about the assembly game, this is it. This is Adrian's magnificent game that we are going to present in detail later on. It's a racing game. This dot is your car, and all you try to do is not to fall on the road. Let's go back to our basic language game first. In order to load the game on the ZX81, you need to convert it to a P file. You can do that using this little program here called ZX Token by XavSnap. You just select the text file or else the plain basic code, and it converts it to a P file. Then you can just drag and drop the P file into your ZX81 emulator, load it and run it. This game is like a fruit machine. You can use other programs too for the conversion, such as ZX Text to P, which works wonderfully. The game is a slot machine, as the name indicates. It produces 3 random numbers, which refer to colors, and when you get 3 similar fruits, you win points. Otherwise, you lose points. In order to play the game on a real ZX81 machine, you will need an external tape cassette player. In our case, we will use a smartphone. The data can be thrown inside with any device that can play WAV files. To convert the P file into WAV, you can use this magnificent program here called ZX81 Tape Converter. You just open the P file and save it as WAV. Then you move the WAV file over to your smartphone and simply connect it to your ZX81 using this lead cable here. If it doesn't work, it's because your device's volume is very low. Use an amplifier or connect it directly to your sound interface and crank it up. I found a lovely game on the web written by John Kingsman for the Spectrum. Software written for the Spectrum obviously do not run on the ZX81, as the ZX81 has much less memory and the architecture is much simpler. But since they share the same microprocessor, I thought that it should be possible to port it to the ZX81. I gave it a try, but I failed. But fortunately, I was following a guy on YouTube who seems to be a big fan of the ZX81, and he's very clever and very familiar with assembly, and I managed to intrigue him enough to undertake the project, and surprisingly, he did. And not only he undertook the project, but he managed to accomplish it and improve it. What a guy! Okay, let's have a closer look at what he has done. So, this is Adrian's code. We are going to use Sublime Editor. I have tried many IDEs and many editors, but this is my favorite one because it doesn't require installation, which I despise. It is fast, reliable, low in radiation, and does not break your balls by popping up syntax suggestions all the time. Starting from now and for as long as this video lasts, we are going to go very technical and nerdy, and basic knowledge of computer science and assembly language are required in order to comprehend the following analysis. So I might make mistakes trying to analyze the code. If I do, Adrian will excuse me and post below the correction as a comment. Okay, let's start. Whatever has the Greek question mark is a comment, semicolon. So at the beginning he includes some other assembly files, the character codes and the original ROMs included in the ZX81. Here he defines some stable values. For example, the width of the rod will never change during play, and here he defines some bytes, some characters and some strings. Here he sets this command equal to this command, and the program starts with a print byte function. Okay, let's bring up the instruction set of Z80 to have them handy here. And as you can see, our first command just pushes register A, F are the flags, it pushes register A into the stack. The ZX80 has one register which is called SP. It is something like a pointer pointing to the stack. The stack is a specific place in memory where you can store values and call them back quickly and efficiently with a pop command. So anyway, this command pushes the contents of register A into the stack and then increases the pointer by 2. In case you want to push something else to the stack, it will push it to the next address, so you don't overwrite your previous push. Our next instruction is called print at. Call jumps to that label. If you search our code, you won't find another print at label in our whole code. There's only one match, which is this one, because this command is embedded in our ROM files. Here it is. Print at sets the location of the cursor on the screen, so our print command can put the character selected on that particular location set by print at, and this works with row number and column number. Our new instruction copies the 2 bytes from SP register into A. A is also called accumulator, and once again increases the pointer by 2. The register SP has 2 bytes, that's why it increases by 2 each time. Our next instruction pushes A into the stack. Our next command is an AND. AND is an instruction that takes an 8-bit input and compares it with the accumulator. It checks to see if both are set. If either one is reset, the resulting bit in the accumulator is 0. So what it basically does is it takes this number, which is the number 214 decimal, and if A is not 240, it will set the accumulator with a value of 0. And then we have 4 of these instructions. So what those 4 commands basically do is that they move over the first 4 binary digits of the accumulator to the next 4 bits of the accumulator. And then we add decimal number 28 or the hexadecimal number 1C to A. And the reason we do that is because our character set starts at 28. 28 is 0 and 29 in decimal, or else 1D in hexadecimal is 1. And 2 must be 30. 1E must be 30, and of course it is. Then he calls our print command, which prints on the screen on the location that we set earlier with print at command. It prints the first digit of the 2-digit number that we are trying to post on the screen. After that, it pops back from the stack the original value of A and isolates the second digit. And how it does that? With the AND command, by comparing the accumulator with the number 15. And if the accumulator and number 15 are the same, then the accumulator will be set to 1. In the other case, it will be set to 0. And then it adds for one more time the number 28 to our new A, and once again it prints the second digit of our decimal number on the screen, and then the program returns to where it was. In our current case, the program will just go on, but if we had, for example, a call print byte command, then it would return where we left it. So all this part here does what basic language would do with locate and print command. All those lines here are equal to just a small line of basic language code. So tell me, which masochistic, unbalanced, self-torturing creature would prefer this over this? But anyway, let's continue. Intro wait loop. BC is a register with 2 bytes. This means that it is a 16-bit register and we can store numbers like 255. I think that's the biggest number that we can store in an 8-bit. So if we sum up, yes, 255 is the biggest number we can store in an 8-bit location in 1 byte. Okay, so BC is a pair of 2 registers, B and C, 2 bytes long in total. And he just stores the value 255 into the BC register. Now this is very complicated if you want to see which number is stored in B and which number is stored in C. But anyway, let's continue. Decrement BC. This means that it will decrement 1 from BC, which means that our new BC is 254. And then it loads the B number, one part of BC, into the A accumulator, and it has an OR command here. What this basically does is checks to see if A is equal to 0. And if A is 0, it goes to read start key, jump. This means jump to read start key if A is 0. If A is not 0, go to intro wait loop 1, which is here, which means keep looping. So if A is not 0, keep looping, and if A is 0, go to read start key. Now you might wonder, here is JR and here is JP. They are both jump. The difference is that GP is called absolute jump and GR is called a relative jump. This means it can only jump between 128 bytes ahead or behind. Anyway, this might look very strange because it splits the pair of registers into B and C. You might be wondering why he doesn't just push BC into the A register. Well, because A register is 1 byte long while BC is 2 bytes long. So let's assume that the waiting time has passed. The 255 seconds became 0 and we jumped to read start key, which is here. What read start key does is to check which key on the keyboard is pressed. And the way it does that is to load the value of keyboard read port A to G, which we set in the beginning of our code. Here, define keyboard read port A to G, which we set to FD, which is number 253. So it loads the number 253 in the A accumulator. And then we have an in command, which is input. Reads a value from a hardware port. Reads which key you press on the keyboard. And if you see here, we have another label, keyboard read port, which we have already set to FE, which is 254. And let's see what this does. It reads from the I/O port. So why does it say port A to G? It will all become clear to you after I explain. Here we are. The Z80 keyboard ports, which are listed here, each port refers to 5 characters, because probably there were not enough ports to correlate each one with a character. So we have multiple characters correlated to one port. And in our case, we have keyboard read port A to G, which is FD, this one here, FD. We don't care about the second byte, everywhere the same. FD is A to G. So all these keys, 5 keys, correspond to the same port. And which key we want to start our program when pressed? We want the S key. So the S key is the first bit, and that is why it says here bit 1, A. Tests if the specified bit is set. So if S is pressed, continue here. If anything else is pressed or not pressed, jump to intro wait loop where we were. But let's assume that you press the S button, then the program continues here to the main function. Our first command is CLS, which just clears the screen. We load 7 into the accumulator, and we also load 7 into the initial car left countdown, which is a variable that we set in the beginning. Then we load the value 0 into the accumulator, and we set the value of score memory tens, score memory hundreds, score memory thousands, all three to 0. Then we load the value 04FF, which is the decimal number 1279, into the register BC. It would not be possible to load this number into a single register because single registers are 1 byte long, and this number needs 2 bytes. And then we load the price 1279 into speed up level counter, which is the counter for speeding up the game during play, and we reset the BC register to 0. We put the value 9 into the accumulator and set the ROD offset from the edge of the screen to 9. From here till here, we have the code for initializing the ROD and making it move. dfile label is a flexible memory location for the graphics. Anything placed in this memory location will be posted on the screen. We have set our dfile to this number here in the beginning of our program, and we load this number to HL accumulator. This is the ZX81 display file memory, display file access. Anyway, the ROD is scrolling in our game, it's constantly scrolling down. We have seen the LD command, the add command, increment, and here we have something new, DJNZ initialize ROD. Decreases B and jumps to a label if not 0. Note that DJNZ does a relative jump, preserves all flags. So what this basically does is just keeps scrolling down the road till our car hits the road, or we press one of the two buttons that move the car aside. Now, I want to skip forward to this routine, to this label, road left. As you saw in our game, the road shifts right and left randomly. This is the routine responsible for the rod shifting left. So what happens here? Before a new rod is drawn on the screen, we erase the old ROAD as Adrian indicates here. We have examined all of these commands, so there is nothing new for us to discover here. But I want to take a closer look at the new ROAD construction. So let's assume that our previous ROAD is erased and a new ROAD to the left is going to be drawn on the screen. First, we load into the HL register the location of the left ROAD that was set in the main routine, and then we load A not in register HL but in memory address with number that the register holds. Parenthesis refers to memory location. Anyway, I said let's skip over the erase ROAD part. When we draw a new ROAD at the left, we decrement because we are moving to the left and we have to deduct one column. Because if we add one, we go to the right. And then we load the increased value of HL to the new variable left ROAD position. And then we load in the accumulator the offset from the edge, the distance between the ROAD and the end of the screen. We load that distance in the accumulator and we decrease 1 in order to go to 0, right exactly where our screen ends. And we load back our decreased register in the variable. And then we have this interesting command here, cp0. cp is a subtraction from A that doesn't update A, but only the flags are updated. There is a flag, I think it's called 0, and it turns on when we have a subtraction and the result is 0. So what happens here is that CP is going to subtract the number 0 from A, and if the result is 0, which means that A was also 0, then it can move to the left and print a new ROAD. But if our result is not 0, which means that A had a value other than 0, for example 1, because 1 minus 0 makes us 1, then skip the increment or else the construction of the new ROAD at the left and go directly to print new ROAD, which prints a new ROAD straight ahead instead of drawing it at the left. So if you were confused by the way I described it, I will try to say it plainly. This routine here shifts the ROAD to the left, randomly of course, because it could shift to the right. This is predefined elsewhere. But in order to draw a new ROAD at the left, the program must make sure that we have not reached the edges. And to do that, it simply subtracts the distance from our ROAD to the edge from 0. And if the distance is 0, 0 minus 0 makes us 0. And in that case, it prints a new ROAD straight ahead and not at the left. You see here the comment of Adrian says skip inc if it's not at the edge. Because if our ROAD is not at the edge, it means there is space between our ROAD and the edge. There is a gap. So subtraction is not 0. Might be 1, 2, 3, 4, depending on how many characters can fit between our ROAD and the edge. Congratulations, Adrian. Your game rocks. Okay, once we have our code ready, we have to assemble it in a P file in order to load it in the ZX81. We will do that with TASM Turbo Assembler, a 32-bit version that works on Windows. If you see here, our P file has been created successfully with 0 errors. Let's have a look at our list file that has been created. Our assembly code has been translated to machine code. Those here are memory addresses and those here are opcodes and operands. For example, let's check our first instruction, which, if you remember, was push AF in the print byte routine. So our first line of code was push AF, which has now become F5, because if you check our command, which is here, push AF, it has the opcode F5, and that is what we see here, F5. Our next command, call printat, here it is, call XX, it has the opcode CD, which is what we see here, CD. And printat is equal to 08F5, which has been written conversely. The low and the high byte swap position. Our next command is popAF, which has the opcode F1, and that is exactly what we see here. Our next command is again pushAF, as we saw here the opcode is F5, and our next instruction is end F0. F0 is in hex, and we know that because it has the $sign in front. In assembly, the $sign means that the following operand is in hex, so it goes in machine language intact. And end should be E6, and if we check, end is indeed E6. And our last instruction that we are going to examine is RRA, which has the opcode 1F, which is exactly what we see here. If we scroll down in our racing list file, we will see our hex dump, which are the exact same instructions as above, without comments and without the assembly language. Pure machine code in hexadecimal with memory addresses in front. The comments and the labels of our assembly code are not being transcribed into machine code, as they are not necessary for the program to run. The comments are irrelevant to the CPU. They are not needed. Our Z80 CPU only needs to perform the instructions with mathematical precision. The comments were meant only for humans. And if we clean out our hex dump from addresses, this is the actual pure code that our CPU will execute. 59 lines. In each line we have 16 hex numbers ranging from 0 to 255. Each hexadecimal number is represented in binary with an 8-bit segment. Each of the numbers you see is 1 byte or else 8-bit. And if you want to go even deeper, we can convert our hex dump to binary, which is what our computer understands. Our computer understands only two states: power, not power, electricity, no electricity. If we check, for example, the first instructions that we examined, CDF508, there they are, CDF508, and the next one is F1, F5, E6. F1, F5, E6. For brevity and economy reasons, this online converter has converted the number 0 into plain 0, although it should have converted it to 8-bit 0. And number 2 in binary is written like this. And the next one is 0, is written like this. And the next one is B1 in hexadecimal, which is this one in binary, 10110001, 10110001. And the final one is 43 in hex, which is 10000011, 10000011. And this is what our computer understands. This is our code, fairly small and simple compared to what it does. Okay, that concludes today's video. I wish to everyone good luck and stay tuned for our next project.